Good morning. Good morning, everybody. I will start with the next presentation. The next presentation is the parametric cost model that we put in place. By the way, this study was done by people who are not, who couldn't make it this morning. So, well, except Arnaud, who is here, but Arnaud cannot be everywhere, so I volunteered to make this presentation. But I was not involved directly in this study. So the agenda, 4 parts. One, we will start with the objectives and the background of this study. Then we will describe the conceptual design that was used to build the model. The third party will be the main part of the presentation, will be the life cycle cost analysis, and then short conclusions. The objectives and background for this study was to build a comprehensive parametric cost model. Obviously, it was to be suited to underground H2 gas storage. It had to be simple in terms of assumptions. We wanted it to be high-level cost estimates with clear and transparent approach, and we wanted to split between injection and withdrawal flow rates on one end, and H2 cost, H2 storage volume on the other hand. And this is something which I think it's very important in this study. I will come back on that. The cost model was then used for ranking the different possibilities at the European scale, and then it was used in next study, and this will be presented by Arnaud in 15 minutes. So basically, this cost model was used for this study. It's not something that was done for engineering, although you could use it as well for a very rough cost estimate as a pre-feasibility stage, for example. Let's move to the conceptual design that we have built and used then for this cost model. We wanted to be very simplistic, very transparent, so we proposed two conceptual designs, one for porous media and one for soil cavern. And we took into account the different aspects of a concept, of a project, with production and injection and control wells architecture, a high-level description of H2 process facilities, so above ground is also taken into account, of course. And then we made assumptions regarding the outline project development plan, the risks, etc., the schedule. And this was done for both soil caverns and porous media storage units. The first design was for soil caverns. The key assumption is that the last cemented casing shoe is at 1,000 meter depth. The cavern diameter is about 80 meters. We made assumptions on the solution mining flow rate. And then we took average values for everything regarding the leaching parameters and the cavern design. And this is on the sketch on the right-hand side. I will not go into those details, but this is available on the report that you can find on the website. We had 3 cases, one medium case, and then one low case and one high case. But all 3 cases were describing the same working hydrogen gas for the total, which was 250 million standard cubic meters as a working gas. But in the low case, for achieving this target, we had four caverns. In the medium case, we had 8 caverns, and for the high case, 16 caverns. Well, the peak withdrawal rate was about the same for the 3 cases. The cavern working gas volume per cavern was obviously different. And then the working gas total gas ratio was slightly different, but approximately between 50 and 60%. Now, for the porous media design basis, we used, well, of course, a set of key assumptions that we considered reasonable from an engineering point of view, and we also based our design on statistical analysis that we could find from IGU or CDGAS database, and that's why we proposed a working gas, global working gas of 550 million standard cubic meters. So it's twice as big as the previous one for the Sol caverns. Okay, and then different assumptions that I will not go through those, but the important thing to remember is it's an average case that you can find on European statistics. Just one thing which is quite important: the number of wells was different between the low case, the mid case, and the high case. But it was between 5 and 71, quite a big difference. And we had safety valve in the well, so it's typically what we could say an European design with downhole safety valves. As far as surface facilities are concerned, well, we used very standard technologies and very standard design with a few items for the injection, a few items for the withdrawal. Well, I will not go through that, but compression was included, of course, and compression is quite an important aspect of this cost analysis, flow meters, etc. And the operating envelope between 60 and 180 bars, and different assumptions regarding the flow rate. Regarding the cost estimate methodology, well, basically we used standard methods. Well, as I said, we based everything on the conceptual design, and we used factorization on equipment and parametric model using in-house data. All the costs are given in euros, in 2020 euros. We assume that those storages were built in France. We had no financial aspect. It's an engineering capex. There is no escalation. There is no discount factors, etc. It's a pure engineer work. And the result is what we could assimilate to a class 4 AACE calculation. So which means 30%, 50% accuracy. Sufficient for this kind of work. Well, I will jump this one. Well, we had technical costs, of course. We have also included engineering cost, what we call here engineering management services, and owner costs. Some exclusion, exploration costs, cushion gas. I mean, the hydrogen that you have to inject initially as a cushion gas is not included, and hydrogen production is not included. Hydrogen transportation is not included either. This is the same thing, but on a visual presentation. Everything here is included. So we start from direct cost, and progressively we built on this system, and we end up with a total view. Today I will present the capex, and in this capex we had also the abandonment cost included, but separately. And we also included the OPEX as a percentage of the CAPEX. The results, well, before showing the global results, one example, but everything is built on the same logic. One example, which is the main parameters and breakdown for filtering, drying, and compression, and metering unit. This end up with some sort of general formulas that you could. Those formulas, you can find them in the report. So you can inject that, each of you can inject that into an Excel file and build the global model. So we have this kind of formula you see with a few parameters for every single aspect of the storage. So this kind of formula, we have maybe between 5 or 10 of those, and you can build the model with that and get curves, provided you stay in the range which is reasonable, which is the one we have defined. A few results. Let's start with the results are expressed here in units of stored volume, and there is a very important assumption here, simplifying assumption, but I think it's a good assumption, which said that the stored volume, the cost of the stored volume, is linked to the subsurface CAPEX only. And we'll see in the next slide that the flow rate will be linked to something else. But the stored volume is considered linked to the underground only. I think if there is one takeaway of this presentation, it's this. We separated the volume underground and the flow rate above ground. So it's a way to simplify, but it's a way to get better results. You know, if you go into the literature, you will find only one value for the soil cavern, or one value for the porous media. I think it's better to split between two values, like here, but at least we know what we are talking about. And this CAPEX for underground is mainly driven by well count, the number of wells or the number of caverns. And you see the results. Well, it's very small, but you can find this in the report. You see on the left-hand side, it's a soil cavern. On the right-hand side, it's the porous media. And the soil cavern is a little bit is more expensive. There are reasons behind this, and the colors are there to distinguish different aspects of the cost, like leaching plant, etc. And in terms of cost, we end up with something like, you see, between 10 and 20 euros per kilogram of hydrogen. Same for the withdrawal flow rate, and as I said, this is related to the above ground only, and here it's the opposite. The soil cavern is the cheapest, and the porous media is the most expensive. The reason behind that is that we have considered that a treatment unit, a purification unit, was needed for the porous media and was not needed for soil cavern. And this is why yesterday you had 4 hours about microbiology. It's the direct impact is on the cost of today. And again, there's also an impact of the well count, indirect impact of the well count. Now, I think this is my last slide. It gives you an overall view as a conclusion with orders of magnitude for the medium case. Again, the good thing about this calculation of this study is that it doesn't give you one value, one single value. It gives you You see here for soil caverns or for porous media, it gives you five values. And you have to multiply those 5 values by the parameters of your project. Could be the gas capacity. That's for the number 1 line, the first line. It could be the flow rate, and this is the value you have to multiply, and you can find on the line number 2. And then we have also OPEX rates, which are variable or not, variable OPEX rate and a fixed OPEX rate. And with this, you get, I mean, you don't need to build the whole model in the Excel file. You can just use those simple values, and you would get a first assumption, a first assessment of the cost of a project, which will be much more accurate than if you use only one value that will say nothing actually. So that's the conclusion. Be careful. It's better to use this kind of, although it's simplified, it's much better than one value that you can find in consultant reports. There are different cost structures. Surface cost. Subsurface costs are expressed in euro per energy, and are higher for soil caverns. And surface costs are expressed by euros per power, and they are higher for porous media. I already commented that. And those costs have been used in Hystories' energy modeling work, which will be presented to you in a few minutes. Now, if you really want to have only one value, I told you it's not a good thing to have only one value, but if you need to remember and make very rough calculation with only one value, we get 20 euros per kilogram of storage of hydrogen, or 2 euros per standard cubic meter. And this is approximately the same for soil caverns and for porous media. Thank you for your attention.
We have time for one short question.
No, thank you. Louis, the brining plant, is it mobile? Can you reuse it?
Excuse me, I didn't hear the question.
The brining, yes, the brining plant, is it the bleaching? Sorry, yeah. Is it mobile? Can you reuse it for the next location?
Well, in this study, we made the assumption that it was dedicated to the project, so you had to pay for it from scratch. In real life, it could be different. I mean, you could have one leaching plant that you use for the first cavern, and then 20 years ago it's still there and you use it again for another cavern. But this is not the assumption here.